So in this particular question, we have to verify that the product of A and B, and when we take the transpose of it, is simply equals to B transpose times A transpose. So we first begin by finding out the product A, B. So we take the column matrix 1, negative 4, 3, and then multiply it to the row matrix B, negative 1, 2, 1. Now, as you can see that the matrix A is of order 3 cross 1, while matrix B is of order 1 cross 3. Now, since the number of columns of first matrix A is equals to the number of rows of matrix B, so multiplication is possible, and after multiplication the new order of the matrix is going to be 3 by 3 matrix. So let's perform the multiplication. So this is equals to, so in order to find out the first element, so what we do, we'll consider the first element, the element in the first row of matrix A, and multiply to the element in column number 1 of matrix B. So 1 times negative 1 is negative 1. Then to find out the next element in the first row, so what we do, we take the element in the first row of matrix A and multiply it to the element in the second column of matrix B. So 1 times 2 is going to give us 2. Similarly, we'll multiply 1 with 1, so that would give us 1. So following the algorithm, we should get negative 4 times negative 1 is positive 4. Negative 4 times 2 is negative 8. Negative 4 times 1 is negative 4. 3 times negative 1 is negative 3. 3 times 2 is 6. And 3 times 1 is simply 3. So this is our matrix AB, the product of A and B. Now what we have to do, we have to take the transpose of our matrix AB. So we take the transpose of it. So transpose is what? The rows get transposed to columns and the columns get transposed to rows. So we consider the row, the first row having the elements negative 1, 2 and 1, and transform it to column number 1. So in column number 1 we'll have negative 1, 2 and 1. Then we consider the elements in the second row, which is 4, negative 8 and negative 4, and place it in column number 2. So we'll get 4, negative 8 and negative 4. Then we consider the elements in the third row and place it in the third column. So that should give us 3, 6 and 3. So we have the transpose of the product of AB. So let's keep it aside and let's name it as equation number 1 for the time being. Now we have to find out A transpose and B transpose. So let's copy these values. So we have A transpose. So we have A. So our A transpose will be, the column matrix will get converted into a row matrix. So we'll have elements 1, negative 4 and 3. So this will be our A transpose, and our matrix B, when we take the transpose of it, the row matrix is going to become a column matrix having the elements negative 1, 2 and 1. Now what we're going to do, we're going to multiply B transpose to A transpose. So let's rewrite the matrix here, where we have negative 1, 2 and 1. And matrix of A transpose is 1, negative 4 and 3. So now we are ready to multiply. This again follows the same algorithm, and this is going to be a 3 by 3 matrix. So negative 1 times 1 gives us negative 1. Negative 1 times negative 4 gives us a positive 4. Negative 1 times 3 gives us negative 3. 2 times 1 is going to give us positive 2. 2 times negative 4 is going to give us negative 8. 2 times 3 is going to give us 6. 1 times 1 is simply 1. 1 times negative 4 is negative 4. And 1 times 3 is positive 3. So this is the value of B transpose times A transpose. So let us compare the two matrices. So this is going to be our equation number 2. So when we compare 1 and 2, so we see the elements are in, the respective elements are exactly the same. So this proves that when we take the transpose of a product of a matrix, then the resultant is equals to taking the individual transpose and multiplying them in this particular fashion. We can even extend it. If we have three matrices and find the product and then take the transpose, then this should be equals to C transpose times B transpose times A transpose. Now in this particular question, we are provided with a matrix, a 3 by 3 matrix, and we have to express it as a sum of a symmetric and a skew-symmetric matrix. So let us consider this matrix to be A. So whenever we have to convert or express any matrix as the sum of a symmetric and a skew-symmetric matrix, so this is the form that it needs to have: A plus A transpose plus half of A minus A transpose. The first half will be the symmetric part, and the second half is going to be the skew-symmetric part. Okay, so we have to find out the symmetric part first. So for that we will need to find out the value of A transpose. So let us do that. So we have A here, so we need to find out A transpose. In order to do that, what we do is we consider the element in the first row, which is 3, -2 and -4, and place it in the first column. So we have 3, -2, -4. Then we consider the element in the second row and transform in such a way that it gets placed in the second column. So we have 3, -2, -5. And finally we take the elements in the third row and place it in the third column. So we have -1, 1 and 2. So that gives us the A transpose. Now that we have the A transpose, so we're going to add A to its transpose. So that will be, so let's rewrite the matrix. So I have 3, -2, -4, 3, -2, -5, -1, 1 and 2. And we're going to add it to its transpose, which is going to be 3, 3, -1, -2, -2, +1, and -4, -5, and +2. So let's add it up, and this is going to be equals to, so 3, we're going to add the corresponding elements. So 3 plus 3, the first element is going to be 6. -2 plus 3 is going to be +1. -4, -1 is going to give us -5. 3, -2 is going to be 1. -2, -2, -4. -5 plus 1 is going to give us a -4. -1 plus -4, so it's simply -5. +1, -5 is going to give us -4, and 2 plus 2 is going to be simply 4. So this is A plus A transpose. Now here we can observe, for any given matrix to be symmetric, it should follow that each element Eij must be equals to Aj. So let us verify it. So let us consider an element in the second row first column, which is 1 here. So we have A to 1 equals to 1, and by definition it must be equals to the element in the first row second column. So the element in the first row, this is the first row, and the second column is also 1, so this is true. Let's take another one. So we take this element, which is the element in the second row, third row second column. This is -4, and this must be exactly equals to the element in the second row third column. So this will be the second row and the third column, so this is also -4. So that means this is indeed a symmetric matrix. Now let's find out A minus of A transpose. So what I'm going to do, I'm going to copy this part and place it here, and I'm going to replace this plus sign by a minus sign. Let me pull this a little down. Okay, so let's find it out. So 3 minus of 3 is going to give us 0. Negative 2 minus 3 is going to give us negative 5. Negative 4 minus negative 1. So this is negative 4 plus 1. So this is negative 3. 3 plus 2 is 5. Negative 2 minus of minus, which is plus. Negative 2 plus 2 is 0. Negative 5, negative 1, negative 6. Negative 1 plus 4 is positive 3. 1 positive 5 is 6. And 2 minus 2 is 0. So this is our A minus of A transpose. Let's quickly check that if this is indeed a skew-symmetric matrix. The definition tells us that if we take an element Aij, that must be exactly equals to the negative of Aj. So for example, let us consider the element in the second row, third column. So element in the second row, third column is negative 6. And this value must be exactly equals to the negative of the element in the third row, second column. So what we have in the third row, second column, which is positive 6. So this is equals to negative 6. So this means this is a skew-symmetric matrix. Also, the skew-symmetric matrix says that the diagonal elements are always equals to 0. So we have a skew-symmetric matrix here. So now that we have both the symmetric and the skew-symmetric part, so we're ready to express the matrix A as the sum of the symmetric part. So our symmetric part is, let's pick this up and place it here, plus half of the other half will be the skew-symmetric part, which we calculated just now, and let's place it here as well. And this is going to be our final answer. This is the final answer. So we have matrix A expressed as a sum of a symmetric and a skew-symmetric matrix. So in this final question, which is very much similar to the previous one, we are provided with a matrix A, and again we have to express it as a sum of a symmetric and a skew-symmetric matrix. Let us quickly begin by finding the transpose of A. So A transpose will be, we consider the elements in the first row and write it in the first column instead. So 0 to be negative 2. For the elements in the second row, we'll place it in the second column, and for the elements in the third row, it will come in the third column. So there we go, we have A transpose. Now what we do, we add A and A transpose together, A plus A transpose. So let's do it. So 0 plus 0 is going to give us 0. Let's write it down. Then we have 2B plus 3, and negative 2 plus 3A. Then we have 3 plus 2B, and 1 plus 1, and 3 plus 3. Then we have 3A minus 2, 3 plus 3, and negative 1, negative 1. This is going to give us 0, 2B plus 3, 3A minus 2, 3 plus 2B, I'm running out of space, push it a little to the right. Now we have 3 plus 2B, 2, 6, 3A minus 2, 3 plus 3 is 6. Let's rewrite this 6. So 6. And negative 1 and negative 1 gives us a negative 2. So this is our symmetric part. Then we find out the skew-symmetric part. So A minus A transpose. So we'll have to write it down. So let's pull matrix A downstairs. So this is our matrix A. Then we subtract A transpose. We subtract E transpose and let's find out the value. So this is going to be 0 minus 0 is 0, 2b minus 3, then negative 2 minus 3a, 3 minus of 2b, 1 minus 1 is 0, 3 minus 3 is 0, 3a minus of minus 2, this is going to be 3a plus 2. This is simply 3a plus 2, 3 minus 3 is 0, and negative 1, positive 1 makes it a 0. So we have this skew-symmetric part as well. Now let's rewrite it. So let's take this matrix. Oops. This is... So we have A matrix is equals to half of the symmetric part plus half of the skew-symmetric part. So this is matrix A expressed as a sum of a symmetric and a skew-symmetric part. Let's quickly verify. So Aij, okay. So this portion must be equals to this portion. Yes, they're matching. And 3a minus 2 must match with 3a minus 2. That's good. Then the 6 must match with the 6. Okay, so this is a symmetric matrix. That holds. Then for the second half, the diagonal elements are 0. But then again, we have to verify. So negative of 2b minus 3 is 3 minus 2b. This one matches. Negative of 2 minus 3a must be positive 2 plus 3a, and negative of 0 is 0. So there we go. So we have expressed matrix A as a sum of a symmetric, and a skew-symmetric matrix. That's it.